Hello, and welcome to Stats Magic Lecture 1, the very first. Now, because it's the first, I want to take a second to quickly lay out what my goal is here. I'm not trying to teach a bunch of statistic methodologies. That is many courses worth of material put on by people who actually get paid for that. Instead, I just want to help demystify, increase stats intuition, and get to talk about some fun stuff along the way. This lecture goes well with a coin toss, with dice rolling, and with roll up the rim. Ready to get started? Statistics is the answer, but it is not what you think. Why would I start with this? I have spent a huge amount of time thinking about numbers and statistics and what it all means. I've spent a large amount of time talking about it with people who hate numbers and statistics. I have answered so many questions about it, and the question is usually, yeah, close, but no. Again, why am I doing this? Two reasons. First, because statistics is a vital part of research, but it is like a soup recipe. If you put garbage in, it is going to taste like garbage. Yes, a soup recipe is a pretty important part of making soup. It gives structure and guidance when you don't know what to do, but that's it. It tells you the ingredients you need and what to do to get something else. Soup. You mistreat the recipe, you use the wrong ingredients, you do the wrong thing, and you could get some really bad soup. Statistics is the soup recipe. It gives you structure and guidance. It will tell you what you need in your data and what to do with it to get something out of it. If you have this data, then you do that to it and it will get you that other thing. The second reason is because it feels scary, but it isn't. Stats is a soup recipe, but that recipe is actually for magic, not soup. It feels scary, has been hated at times, is hard to understand, but it does some pretty cool stuff. One of the places I talk about statistics most frequently, with strangers anyway, is on airplanes. Actually, my dad writes plays, and there was a character in one of his plays that was based on me talking to strangers about statistics on planes. It does happen very frequently. So let me start by saying man was not meant to fly. If we were, we would have wings. That means it is not crazy that I am super scared of it. It's probably an evolutionary advantage to be afraid. Just think, you can get a flat tire or even complete engine failure in a car and just pull over. It's all good. You could be in a fender bender in a car, and there's a whole range of accidents from fender bender to catastrophic. In a plane, there's way less options. You're going down, it's going to crash. Time and time again, when my fear becomes visible, strangers on planes tell me, it is statistically more likely to die in a car crash than a plane crash. And guess what my answer to that is? Fudge off! No, the answer is close, but no. First, you're not actually talking about statistics, so get that word out of your mouth. This is probability. There is a greater probability of being in a car crash than in a plane crash. It is more likely, but you don't actually need a soup recipe for that. Could it be stats? Well, yeah, it could. You could absolutely collect some data. Maybe accidents per person per hour, compare cars to planes, maybe find that it's significant or not, but that is not what people are talking about. This is probability. Now, probability is the foundation of statistics. But like not all cats are tigers, not all probability is statistics. Whew, deep breath. I promise we're going to get back to it, but we're headed on a probability tangent. For a more detailed look at probability of a coin toss, go ahead and watch the video on that. We're just going to go through this real quick. This is a coin. This coin has tails, it's a loon, and it has a head. King Charles looking dapper. You toss it once, it will be heads, or it will be tails. Mutually exclusive outcomes. In your mind, you're probably already assuming, well, it's 50% heads, 50% tails. That would be nice and easy on the brain. But it's not true for one coin toss. This is insight from many other coin tosses prior, not this one now. Probability does not exist for a single event. It is going to be 100% loon or 0% loon. Now if we do this 10 times, each time it's 100% loon or 0% loon, but we can start counting how many times we get a loon as compared to the king. So here we go. Heads, 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 tails, heads, tails, 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 tails. We get 4 heads, 6 tails. Assuming no prior knowledge, we now would say it's 60-40. Now we do have a probability. But wait a second. We got repeats. 3 heads in a row? Oh, and then 5 tails in a row. Dang, is this coin weighted? Relax. 10 is probably not enough reps to actually see the true probability of each flip. Every coin toss is independent. The outcome is mutually exclusive. 5 heads and 5 tails is one possibility, but it's driven entirely by chance. What happens if we do more? Now, I actually did these, but with a simulator. I don't have the dexterity for that. I barely made it through 10. It gets closer and closer. At 100 tosses, we see 53 tails and 47 heads. That's 53 to 47. 1,000 tosses, we have 507 to 493. That's 50.7 to 49.3. 10,000 tosses. Now here is an important benchmark because at this point, 4,956 to 5,044. If you were to round this to a whole number, it would be 50-50. At 100,000, we have 49,913 tails, 50,087 heads. And again, this is going to round to 50-50 pretty easily. And by a million, even more so. I did all of that in R because I'm not going to toss a coin so many times. I got programming chops. Who has time for that in real life? But if we do not know the true probability of an event, and we do not know how many times we have to repeat it to get the true probability of an event, what the heck do we do? Will we ever know? We are like soup chefs with ingredients and no directions. Before we move on, I'm going to throw one more example at you. Roll up. We all know and love roll up. We're going to do a deep dive on this next week, but for now we'll touch the surface, and please go ahead and watch the video on dice rollin' for more on 1 in 6 chances. So roll up says right on it that there's a 1 in 6 chance to win. For the purposes of this experiment, we are going to consider all versions of winning to be equivalent and the same. A win is a win, whether it's to an ID buzz, a weekend vacation, or a donut. So Tim Horton says the chance of winning is 1 in 6. Now you're going to go ahead and buy 10 cups for yourself. And the results are lose, lose, win, lose, 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 win, lose, lose. 2 wins! Winner, winner, chicken dinner! I hope one is an electric minibus. So that's 2 wins out of 10 tries, or 1 in 5. We know that increasing the number of tries will help us out. In fact, we could say that increasing the number of cups that you roll up is going to increase the reliability of the probability that you get out of it, meaning it's more trustworthy because it's more stable and consistent. We would also say that it's more valid, by which we mean it's more true. So hold that in your mind, grapes, because in-fly statistics claims to be a recipe for making sense of, but if we do not know the true probability of an event, and we do not know how many times we have to repeat to get the true probability of an event, in other words, this is going to help us deal with all the uncertainty in this big old pot of soup. So we're going to start thinking about this a little bit bigger. If stats is this big dark rain cloud, then bam! There are 2 general fields that strike out of there: descriptive and inferential statistics. The descriptive ones are about describing your sample. You can look at the central tendency, that's your mean, median, or mode. You can look at variability, being standard distribution or interquartile range. And maybe you want to look at your sample in a scatter plot or even a dreaded pie. Now, inferential statistics are going to look at making conclusions about the population based on your sample. They are taking it a step further than descriptive statistics, which might be an estimate of population descriptives, and inferential statistics are going to try to say something about the data and then infer that that applies to the population. This is going to add hypothesis testing and p-values. You might still want graphs, but now you're going to be using the graphs to look at distribution or relationships, and we finally might be able to say if Tim Hortons is lying about the proportion of winner cups. Here is the Oxford Dictionary definition of statistics: the practice or science of collecting and analyzing numerical data in large quantities, especially for the purpose of inferring proportions in a whole from those in a representative sample. Once more, for those in the back, we are inferring proportions in a whole from those in a representative sample. Thank you, Oxford Dictionary, for making my point. So let's turn our probability into statistics. We're going to start by making an experiment. Real quick, we have options on where we could take this. For first level, I'm thinking we could just collect a whole bunch of cups and just check to see if Tim Hortons is lying. They say 1 out of 6. But is that true? This is partially straight up probability, and that we're just trying to get enough repeats to see if it approximates what it should. But there are statistics that we can use to help us determine if what we found in our sample deviates from what Tim Hortons said should be there. If we want to go even deeper, maybe we are going to ask whether Tim's gives more winners to rural communities to help boost their brand as a small town coffee shop. Whoa. Now that is a question I want to ask. Whew, one more deep breath. Dang, there we go. From a proportion or a probability to a statistic. Now we're not going to talk exactly about how to conduct this test. It's going to be a chi-square of sorts because that's the one to use for proportions, which is essentially going to look at as observed minus expected divided by expected to make a new proportion. The mechanics don't matter. I'll tell you, there is a tool. It's your chi-square soup recipe that will give you something that will tell you whether what you see is different than what you expected or, nah, this is in the range of sameness. To tie up this thread, I did make some data in R just so that we could test it and have some kind of result just for funsies. We're going to go into this in more depth next week. But in this result, we found 169 out of 1,000 rural cups were fake winners, and 164 of 1,000 urban cups were fake winners. And we know the probability of the sample is going to approximate the truth and not exactly hit it, but just looking straight up at the probabilities, we already see 169 versus 164 is pretty close. Based on the probability, like 16.9% versus 16.4% is very close, especially when we know that 1 in 6 amounts to 16.7%. So our chi-square soup recipe, we're going to call on it to ask this question. Is there a reason to believe that 169 out of 1,000 is different from 164 out of 1,000? And what we find is chi-square equals 0.058, which has a p-value of 0.813. This is higher than the threshold 0.05, so we cannot reject the null hypothesis that there is no difference in these cups. We have found nothing to suggest that buying Tim Hortons from a rural Tim Hortons is a greater chance of winning at roll-up. Now, one more thing. If we are inferring proportions, in this case, proportion of wins for urban Tims and the proportion of wins for rural Tims, then the inference will only ever be as good as our sample is representative. Remember, if you put garbage in, you get garbage out. If you put garbage in your soup is garbage. And it's always going to be worth going back to check your methods to ensure you're getting good data from your soup. Ways that this could be garbage include maybe you have 100 people who are lying for personal gain. Maybe you need to consider cup size because maybe a certain size is more likely to win. We don't know. Maybe we need to make sure that all the cups are roll-up cups and certain locations didn't just run out. All of these things are going to taint our soup. One more thing still. If all we have is the data after the facts, how do we know if it's garbage? Good question. We don't really, but we can look for a few common ways that it could be problematic. One of the ways is to consider what garbage looks like and then look for that. And by that I mean if you can think of a confound or a potential bias, you should probably take steps to check if it's in your data. There are other ways, but I will leave that to you to come up with. And I'm going to leave you with one question. If you bought 100 Tim's cups and all of them were winners, how likely are you to win on the 101st cup?